If you took just a single chemistry class, you've heard that benzene is particularly stable due to its aromaticity. Well, benzene is cute, but it pales in comparison to the massive Kekulene, basically a Chad version of normal benzene, which was long disputed to be a super-aromatic compound. It's so apolar and insoluble that you can only dissolve it in spicy hot solvents and need to measure your NMR spectra at 200 degrees. In today's video, we will travel back in time and deconstruct the original and a modern synthesis of Kekulene. You will be surprised that it's not wizardry and quite simple chemistry, so you should be able to understand if you have a good knowledge of organic chemistry fundamentals. Let me know in the comments if you are able to follow. Before we get ahead of ourselves on super-aromaticity, we need to understand simple aromaticity. In the 19th century, pioneering chemists started to explore the field by doing all kinds of random reactions. They were puzzled that benzene was so unreactive towards addition reactions, even though it was assumed to have a high degree of unsaturation. August Kekulene first proposed the cyclohexatriene structure for benzene in 1865. You might wonder what the big deal was, but remember that at this point in history, today's models and structural understanding did not exist. In one of his reports, which by the way reads as if he just watched my LSD video and ingested some himself, he said that the vision of Ouroboros, the snake that eats its own tail, inspired him to think of the mesomeric structure of benzene. The actual fundamentals and rationale behind aromaticity were discovered some 60 years later with the famous Hückel rule on 4n plus 2 pi electrons. Hückel's concepts remained quite unrecognized for 2 decades, apparently also due to his lacking communication skills, but his contributions made him a cornerstone of organic and physical chemistry in the 20th century. Looking at the molecular orbitals, it becomes clear that 4n plus 2 corresponds to a full set of binding molecular orbitals, resulting in higher stability of aromatic compounds. Upping the ante, the concept of super-aromaticity envisions that macrocyclic conjugation in large polycyclic aromatic hydrocarbons leads to an even increased stabilization of the molecules. In 1951, the physical chemist McWeeny postulated the potential existence of Kekulene. In 1965, so 100 years after Kekule's seminal work, first synthetic investigations were published and the molecule was named in Kekule's recognition. The key question for Kekulene was which electronic model best represented its structure. Is it a simple, localized structure consisting of 6 individual benzene rings? This is what McWeeny hypothesized already in 1951. Or was it actually a super-aromatic structure that is based on 2 connected annuline rings, here in blue and purple, that both satisfy the 4n plus 2 rule? The implications of these 2 setups are quite significant, and one of them relates to the diamagnetic anisotropy. When benzene is placed in an external magnetic field, like during NMR, its pi electrons circulate in the conjugated plane, creating a new green magnetic field that opposes the external light blue magnetic field. This means that if you are a benzene proton, you will feel the new magnetic field in the same direction, leading to de-shielding and higher chemical shift in proton NMR. If you are an outer red proton in 18 annuline, where electrons are delocalized over the whole ring, you will experience the same thing. What changes, however, is the experience for the inner blue proton. Because the induced magnetic field opposes the external one, it shields the proton and leads to a lower chemical shift, even negative in the case of annuline. The implications for Kekulene are clear. If global delocalization is a thing, we should see highly shielded inner protons like we see in annulines. To answer what Kekulene looks like, we have to make it in the lab and characterize its properties. At the end, there's only so much you can compute. We will first look at the landmark old-school synthesis of Kekulene achieved by Staab and Diederich at the University of Heidelberg. Staab is most known for inventing the CDI reagent for hydroxyl and amine derivatization. Diederich, his PhD student at that time, majorly contributed to our current understanding of supramolecular and medicinal chemistry. In a second step, as an evolution to their approach, we will look at a modern entry into their synthesis, which uses a very crazy looking synthetic equivalent. The successful synthesis by Staab and Diederich was based on almost 2 decades of work, and it started with metaxylene, which was nitrated and condensed with benzaldehyde. After hydrogenation of the double bond, which was performed in large scale with 1.6 kilograms of starting material in 50 liters of solvent, the stage was set for a very nice cascade featuring the so-called Pschorr reaction. It might remind you of the Sandmeyer reaction, as it also proceeds via oxidation of the aryl amine to the diazonium, which then undergoes single electron transfer with copper, triggering an intramolecular cyclization. This cascade happens on both sides in one pot, but yields the pentacycle in poor yield only. Interestingly, the Pschorr reaction features use of copper 0 in the form of so-called Naturkupfer C and not copper 1 salts like the Sandmeyer reaction. We now have some of the rings in place, but we need to introduce functional groups on the aryls to create even more rings. To this end, they bromomethylated the pentacycle via an electrophilic aromatic substitution. Then, the benzylic bromide was converted into a thiol in 2 steps through nucleophilic substitution with thiourea and basic cleavage of that adduct. To build the Kekulene scaffold, they coupled the 2 halves through double nucleophilic substitution. This reaction was performed under high dilution conditions with only 1 millimolar concentration. This favored intramolecular closure to the ring instead of successive intermolecular reactions and gave a high yield of 60%. The sulfur was of great use to build the scaffold, but at some point you also have to remove it. To prepare this, the team methylated the dithiacyclophane and then subjected it to base-mediated Stevens rearrangement. This led to regioisomers of the ring-contracted thioether. To remove the sulfur completely, the team explored different methods. The first method was methylation to the sulfonium, which is a great leaving group, and can thus be eliminated. However, they had to explore another route as byproducts were very difficult to separate from the desired product. A much better way proved to be oxidation to the disulfoxide, which was then pyrolyzed at 450 degrees Celsius. As a side note, they also looked into the exotic Ramberg-Backlund contraction to give the olefin. It proceeds via alpha halogenation of the sulfone and subsequent intramolecular substitution, leading to a free-membered ring that can again eliminate SO2. It's quite a miracle they even managed to isolate the 2 mgs or 1% yield of this reaction by preparative TLC. Obviously, this approach was not workable, so they opted for the other one instead. Finally, the product was photocyclized to yield octahydrokekulene. Here they found that using the saturated starting material was vital for success. They initially tried to install the double bond first and only then performed the cyclization, but this was unfruitful. Probably creating the fully planar system up front makes it too rigid. Instead, the aliphatic CH2 groups add the flexibility that is needed to enable the photochemical reactivity of the cyclization. Last, the octahydro derivative was oxidized with DDQ. Just to solubilize the starting materials and achieve the reaction, they used trichlorobenzene as a solvent and let the reaction run for 3 days at 100 degrees. They found Kekulene to be so insoluble that they had to recrystallize it from boiling 400 degree hot triphenylene by quote-unquote slowly cooling that to 300 degrees. Growing Kekulene crystals allowed them to investigate its molecular structure. It was shown to be almost perfectly planar with very low variation in bond lengths, even for the inner protons. Based on X-ray analysis of the bond lengths, they concluded that Kekulene probably does not have globally delocalized electrons or super-aromaticity. What about NMR as an analytical technique? Well, due to its low solubility, the team had to resort to creating deuterated trichlorobenzene and recording NMR spectra of saturated solutions at 200 degrees Celsius to get anything usable. When they finally got some measurements, they found that the inner protons were extremely de-shielded. So basically, the contrary of the delocalized aniline example we've talked about at the start. The protons looked like benzene protons, further suggesting that the superaromatic structure was incorrect. So much for the OG chemistry. Remember the initial PSOR reaction with low yield? In a more modern way, the team of Perez envisioned a clever Diels-Alder shortcut by using this commercially available bis triflate. Addition of fluoride triggers elimination towards a triple bond, which can engage in a 4+2 cycle addition with styrene to form a 6-membered ring. After re-aromatization and release of the second triplet, another Diels-Alder reaction yields 2 isomers, one desired cis-like isomer and a trans one. After some optimization, they managed to increase the yield to 28% with a 2-to-3 mixture of cis to trans. This means the net yield is also just around 11%, so quite similar to the PSOR reaction itself, but you save yourself all other steps in the beginning of the synthesis. Staab and Diederich's synthesis truly stands the test of time, as Perez's team also looked into synthetic alternatives after the first step. It seems even modern methodologies could not improve or even come close to recreating the original synthesis. The ultimate point of Perez's team, by the way, was to perform ultra-high resolution atomic force microscopy, basically making nice pictures of singular molecules. Based on their findings and calculations, they also concluded that Kekulene does not have delocalized pi electrons and that the Clar model with 6x6 pi systems is the most appropriate one. Believe it or not, there are even funkier Kekulene-related molecules being created, such as septulene, but this is where we will stop for today. Let me know if you like this one and which other topics you would be interested in hearing more about. Thanks so much for your support, and until next time.